we evaluate the integral with the limits. If you're great with this in math class, you can go ahead and solve the integral on your own. Otherwise, you can just look it up in a table. If we look it up in a table, we find that our result is k times lambda times y times x in the numerator, y squared times square root of x squared plus y squared in the denominator, and that's evaluated at our limits of L over 2 and minus L over 2. So we fill in plus and minus L over 2 for our x's, so k times lambda. We might notice here that they cancel. We can bring that y out front. So we get L over 2 square root of L squared over 4, so x squared is L over 2 squared, L squared over 2 squared is 4, plus y squared, minus L over 2, minus L over 2 squared is still L squared over 4, plus y squared. So we've got L over 2 minus L over 2, that's going to give us L. K times lambda times L over y, 1 over square root of L squared over 4 plus y squared. Okay, so there's the expression for our y component. We see that it turns out positive. It's not quite good enough to rest on the math. Let's look at our picture and make sure we're good with that. We see that our y component points up, so yeah, we agree that that y component should be positive. So let's write down our answer. Our net electric field vector is the x component, which was 0, plus the y component, which is k times lambda times L over y times 1 over square root of L squared over y over 4 plus y squared. That's in the y direction, so we put a j hat. So there's our electric field above the midpoint of that rod.